All right, hello physicists. Today we're going to be finishing up our material on capacitors, and we're going to be introducing the idea of electrical current. So to start out our review of capacitors, let's just go over the basics one last time. Capacitors store charge. So if you connect up your capacitor across a plus and a minus battery, the side that's connected to the plus will get a plus charge. The side that's connected to the minus, so we're going to close that switch, would get a minus charge on it. Now, the capacitance depends on a couple of things, but the main one that we're focusing on in this class is that it depends on the material geometry. So for instance, in this parallel plate geometry, the capacitance depends on how big the plates are and how far apart they sit. Now, in a real capacitor, and I'll discuss this a little bit more in a second, there are tricks to make the capacitance bigger than just in this sort of idealized model. The capacitor has a charge Q equals CV, and the charge is a positive charge on one plate, a negative charge on the other plate, and so when we say a capacitor is charged, we don't mean that there's a net charge on it. You wouldn't expect to get a Coulomb's law type of electrostatic field out of it. Really, you would expect you have that zero charge, and the capacitance then is determinant of how much charge will sit on your capacitor given a particular voltage. So you can choose a voltage by a 12-volt battery or something like that. And then you have the capacitance, which is depending on the geometry of the material, and that will determine how much charge is sitting on those plates. Now, the other thing that we've gone over is that if you have a bunch of capacitors connected to one another, they can be relabeled and thought of as acting like one single capacitor. So, for instance, if we took these three capacitors together, this is called connecting them in parallel. The charge on each one of these is going to be dependent on the voltage applied by the battery, since all of them have their plus and minus sides connected just by a wire directly to the battery. So when we want to think about the equivalent capacitance, we would just have to add up all of these charges, and it turns out that the equivalent capacitance of bundling together capacitors in parallel is just adding together the capacitances. On the other hand, when we have something in series, where we have one capacitor after another, the overall capacitance of this setup is going to be smaller than the capacitance of any one individual capacitor. And that's because each one of these has a smaller voltage drop across it than the voltage drop of the battery. And each one of these has the same charge on it. And that's because if you start out uncharged, then the minus charge on this plate, for instance, has to be the same as the plus charge on that plate. So in lab this week, hopefully you got some experience with that. Here, I want to recommend to you this video right here. This is a guy who has a channel. He calls himself Electro Boom, and he makes sort of educational comedy videos in the sense that he shocks himself a lot for the enjoyment of his viewers. But in this video, he builds some capacitors, and I want to just show you that the simplest possible capacitor is really as simple as I've said. So what he does is he takes a piece of aluminum foil, and then he takes a piece of mylar or plastic, and then he tapes on top of it another piece of aluminum foil, and then connects up a wire and another wire. And that's it. One wire on the top, one wire on the bottom, so you've got the two sides of that capacitor are separated, and you have the conductor, insulator, conductor That's the structure of your capacitor. And he also shows in that video how you can increase the capacitance by rolling up the capacitor. So it's a really nice example of the sort of simple physics of this situation. I also want to remind you that since it is Friday when I'm posting this, the people who are in class have a quiz, a reflection question, and homework questions. So what we're going to do next, we're going to go over a couple of pseudo quiz questions. I hope we have already, in this video even, talked about what the answer to your reflection question should be. For instance, capacitor is used to store electrical energy that can be released quickly, blah, 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 blah. And these are your homework problems that are due on Monday at the time of class. Okay, this is Picard saying, yes, I love physics. Okay, so first off, let's go ahead and take a look at it's a simple quiz question. If you know the answer, it might be tricky if you don't know where to start. The plates of an isolated parallel plate capacitor with a capacitance C carry a charge Q. What is the capacitance of the capacitor if the charge is increased to 4Q? Well, let's take a look at the formula for our capacitance of a parallel plate capacitor. What does it depend on? Well, it depends on the area of the plates, and it depends on how far apart those plates are. That doesn't depend on how much charge is on the top and bottom plate. So, in this case, the capacitance, if we increase the charge to 4Q, is still going to just be C. All right? All that has changed really is that the C has stayed the same. This has gotten 4 times bigger, so that means you applied 4 times the voltage. So you have 4 times the potential difference across the plate, leads to a 4 times bigger charge. Okay. Now here's a little, let's think again. This is similar to a problem I showed you a couple days ago. It says a parallel plate capacitor with plates of area A and plate separation D is charged so that the potential difference between its plates is V. If the capacitor is then isolated and its plate separation is increased to 2D, what is the potential difference between the plates? Okay, well, let's suppose that, well, let's just see where this comes in. You've got a plus Q and a minus Q on these 2 plates. And presumably that's going to stay the same as we change this D up to 2D. So in this case, the C is changing, the capacitance is changing, but the Q is staying the same. Okay, so what we have is that CV at the initial is going to be CV at the end. So for instance here, if we had epsilon naught A over D times whatever V naught we had, now if our plate separation is increased to 2D, this would be epsilon naught A over 2D times what? Well, I hope you can see that if I put a 2 in the denominator, I need a 2 in the numerator to keep these 2 sides equal. So I'd have to have 2 V naught. Okay. And so, whoops. Okay, so I noticed I had a typo in my slide. Okay, so I hope you realize that we would need twice the voltage to get the same, to maintain the same charge. So the potential difference in this case goes to 2 of the original voltage. So I did a little bit of fast editing on that slide. Okay, one last one for this quiz review. It says capacitor B has 1/2 the capacitance of capacitor A. How does the potential difference on capacitor A compare to that on B when the two are connected in series with a battery for a long time? Okay, well, let's draw this out and make sure that we understand it. So in series means that our capacitor A and our capacitor B are right next to each other. The problem gives us the information that the capacitance of capacitor B is 1/2 of the capacitance of capacitor A. All right. So what could you do? Well, I suppose one thing you could do, you could find the equivalent capacitance. You could then find the charge. You know that the charge plus Q and then minus Q plus Q and minus Q is going to be the same on each one of these. Then you could go ahead and find the voltage. So that's the hard way to do the problem. The easy way is to just look at this and say, oh, look, this one has the same charge on it as that one. So in this case, for the parallel, or for the series circuit, if it were a parallel circuit, of course, each one of them would just have the same voltage, but a different charge. But in this case, they have the same charge across them, but different voltages. And so you have your QA equals QB, which means that your CA times the VA, capacitance of A times the voltage across A, equals the capacitance of B times the voltage across B. Now I can say, look, if my capacitance of B, CA, VA, is just going to be capacitance of A divided by 2, I can go ahead and divide both sides by the capacitance of A, and I find that the voltage of A equals 1/2 the voltage of B. And this is sort of a general a general observation, which is that for these series circuits, the voltage is going to be the biggest for the smallest capacitance capacitor. Okay, the potential difference is bigger for the B because it has a smaller C. Okay, so going back here, the voltage across B is 2 times the voltage across A. And it's asking about the potential difference on A in terms of B. So we have the voltage difference across A is 1/2 the voltage difference across B. Okay, let's see which one is the answer there. The potential difference on capacitor A is 1/2 that of the that on capacitor B. There we go. All right. So there we go. Now, something that I covered briefly in the last video, but which I just want to hit one more time because we're reviewing, is the idea of energy in a charged capacitor. Now, I didn't give you a lot of homework on this, but remember what was happening here is that the potential energy is how much work you would have to do on all those charges to assemble them onto the plus and the minus sides of the capacitor. And the strange thing about this, and the reason why you come up with a Q squared over 2 instead of just like depending on Q itself, is that that we're integrating, and as you put more charge onto the capacitor, the voltage gets higher and higher. So putting more charge, each additional little piece of charge requires more work than the last piece of charge. Okay, so that's the physical interpretation of what's going on here. The little differential work is the voltage times the extra differential charge that you're putting on, but the voltage itself depends on the charge on each plate. And so what you're doing then is integrating from 0 charge up to some final charge Q, and then your work depends on the Q squared over 2C. Now, in terms that we can measure in a circuit, it's more convenient for us to say that the potential energy depends on C and V squared. And remember, all I did there was just saying that work, which is U at the end of the day, equals C times V squared over 2C. Okay, then I square these out, so this is C squared times V squared, and then U is just 1/2 CV squared. Okay, so that's where this comes from. Now, in your lab this week, what I asked you to do, we looked at these experimentally, where we put a voltage source and then connected 3 capacitors in series. This one was the tricky one. And then we looked at a voltage source and we connected 3 capacitors in parallel. And what we did with each one of these was to calculate the amount of charge on each plate. Then for this one, we took the average charge and divided it by the battery and got our equivalent capacitance. For this one, we added up the total charge by adding the charge on each plate, just using our Q equals C times V. And then we found the equivalent capacitance in that way. Now, the second part I wanted you to say is after you already have that equivalent capacitance. Okay, so just to remind you, in this case, this is a series circuit, so the equivalent capacitance would be 1 over C1 plus 1 over C2 plus 1 over C3. And then for our series circuit, our equivalent capacitance would just be C1 plus C2 plus C3. Now, what I asked you to do at the end of the lab this week was to calculate out what the potential energy on each one of these capacitors was. Now, this was easy for our capacitors in parallel because they all have the same voltage, they have different capacitances, and you would just put in 1/2 C3 times the voltage of the battery, 1/2 times C2 times the voltage of the battery, 1/2 C1 times the voltage of the battery. And you could do that because each one of these experiences the same potential difference, since all of these wires that are just connected are at the same potential. Now, on this case with the capacitors in series is a little more complicated because the V1, V2, and V3 are not the same. They add up. V1 plus V2 plus V3 should add up to that voltage of the battery, but they're different numbers typically, and so to calculate the energy of each one of these capacitors, you'd have to use 1/2 C1 V1 squared, 1/2 C2 V2 squared, 1/2 C3 V3 squared, and so that you would get those individual energies on each one of those capacitors, then add them up, and that would give you the energy of the entire circuit. But what I want to stress is that in each one of these cases, okay, if you just wanted to look at the total energy of the circuit, it would be legitimate to say 1/2 C equivalent times V of the battery squared. And so if you know the equivalent capacitance, you can just directly find what your potential energy stored in your circuit is. Okay, so that's a little bit surprising, but an interesting result. In our last video, I went over a couple of the homework problems that I thought were tricky. So I will be doing this one in class today, but if you're just watching the videos, I encourage you to go to the end of our last video and look for this, because I do this one on that video. I also looked at a little bit of these types of problems where you have both parallel and series circuits. Now, I put this picture up. This slide is from our last homework, or our last video, more or less. But I didn't discuss this, so I want to just spend a little bit of time noticing that these circuit problems are sort of topological. And that sounds like a fancy word, but what I mean by that is you can sort of twist the circuit around and move the parts around as long as you don't break anything. Let me show you what I mean. So this circuit right here, I can write it in a way that is hopefully going to make it clearer how you would find the equivalent capacitance. So I can write it like this. There's my C1, here's my C2, and then after those comes C3. Okay, so if I wanted to find the equivalent capacitance of this, here's how I'd do it. I would first treat this as a single capacitor with a capacitance of C1 plus C2. Then, once I've done that, it looks to me like I have a capacitor in series with another capacitor. And so I could find the equivalent capacitance of that by having my C equivalent of the whole circuit equals, well, I would have to do my 1 over C1 plus C2, because those are acting as a single capacitor, plus 1 over C3, and then I would have to take 1 over that whole thing. So I would take this and take the inverse of it. So that would give me my equivalent capacitance of this whole circuit. Now, what might not be obvious to you at this point is that circuit C will actually have exactly that same equivalent capacitance. Now, how is that possible? Well, take a look. What I want to do, I want to just flip this over. So instead of drawing this capacitor over here, I'm just going to imagine taking it over. This is all just connected by a wire. You're just moving it over to the other side. Okay, so I'm just taking this and I'm moving it over like that. Okay, why does that help me? Well, because it allows me to see that this looks a lot more similar to my first example than I may have realized at first. So C3 is directly connected to the plus, and then the C1 and C2 are both connected equally close to the minus. They're both connected just by wires to C3. So in fact, C1 and C2 are in parallel. So look, again, I could treat this as an equivalent resistance of C1 plus C2. Then I could find my equivalent capacitance of the entire circuit by treating this as a capacitor and treating that as a capacitor in series, and I would find that the equivalent capacitance of my circuit would be exactly the same as before. So I've given you these as a homework problem. I encourage you to just draw them all in a similar way such that you can see what the trick is in this problem. You know, ultimately, they should all be the same capacitance. So I'm giving away the answer there, but I want you to draw the pictures so that you can see why that is. All right, same idea in this. I treated this in the last video briefly, but just to, put more flesh on the bones of what I said last time. If you've got your C1 that's 10 microfarads, C2 is 5 microfarads, and C3 is 4 microfarads. How would you find the equivalent capacitance of the whole thing? Well, you'd first find your equivalent capacitance of that. So your equivalent 1 over your C equivalent would be 1 over 10 microfarads plus 1 over 5 microfarads. Okay, so you'd find this, and then that would be in parallel with C3. So ultimately, once you find this equivalent capacitance, the equivalent capacitance of the whole thing is just going to be whatever you found here plus 4, because the equivalent capacitance of capacitors in parallel just requires you to add the two. All right. So that's all we're going to say about capacitors right now. We will use them throughout the semester, so we can't really forget about them. But what I want to do now is just to give you a little preview of where we're going with this. The interesting things that happen in circuits are not just electrostatic circuits, where stuff is not where we look only after our charge has settled down. So that's all we've looked at so far, is electrostatic circuits where you charge up a capacitor and we only think about the charge on it after all of our charges have stopped moving. What we're going to be thinking about next is what is happening when our charges continue to move. And to describe that, we're going to have to think about a quantity called current. Now, what is current? Current is the amount of charge that passing by a given point in a circuit per unit time. Okay, so our wire is filled with a bunch of charges. Okay, and I've told you that the charges that usually move, for instance, in a metal are in fact the electrons, not the protons, but you can equivalently think about plus charges moving this way or minus charges moving that way to give you a current along in the plus x direction. So that's confusing, but I don't want us to get hung up on that at this moment. The units on current are going to be coulombs per second, or amps. Ampere, of course, is we've already seen him. He'll come back again with Ampere's law, which relates the magnetic field in a region to the amount of electrical current that's in the region. So it'll be like the Gauss's law of for magnetic fields, but the amp is just a coulomb per second. So it's telling you how much charge is passing by your cross section of the circuit in a single second. And so this current is just telling you about a slice through your circuit, and then you're counting how much charge is passing each second. Now, I don't want you to get too confused about this, because for the moment, it's okay for us to think about sort of a water analogy. If you have a bunch of water that's coming into a pipe and it splits off into two pipes, the amount of water that's coming in per second into this pipe has to equal the amount of water going out per second into the pipes that it splits off into. So for instance here, if we start out with some current and there's a junction where the current splits off, the current coming in has to equal the current going out. Now this is going to be a little bit complicated because we're eventually going to have to think about the signs on the current. So we're going to have to apply, like you could have a positive current going to your right is the same as a negative current going to your left. So that'll be a complication, But just for today, we're not going to put in any numbers. I just want you to get the general idea. The current coming in has to equal the current going out because it's an amount of stuff. Now, to give you like a specific example, it might be worth pausing the video and just drawing this structure so that you can fill in the numbers with me as I go. Did you pause? Okay, I'll trust you. So let's see how this works. Look, you've got a 2 amps of current, 2 coulombs per second coming into this wire, 3 coulombs per second going into that wire. Here is where they meet. Now we might ask, how much current is in this wire? Well, it has to be 2 plus 3 amps. So this would be 5 amps going this way. Okay, so this wire has fed in, that wire is fed in, and there we go, we've got 5 amps. Now, I'm looking at this and I say, okay, well that 5 amps then is going to come and it's going to split off into 2 directions. Ugh. Have they made things hard for me? Am I done? Well, not quite, because look here. Here you have 2 amps coming out and 1 amp coming out. So that tells you how much current must have come in to this junction. So 1 plus 2 is 3 amps must be going here. And we must have 2 amps then going there. Why? Because all of this 5 amps is going either up or down, and so 3 plus 2 is going to be 5. Okay, now let's look here. We've got 4 amps here, we have 2 amps here. Those are going to combine together and go into this wire. So 4 plus 2 would be 6 amps. And then right here, we must have the 6 amps and the 2 amps coming in, and then they go right here. So 6 plus 2 would be 8 amps. Okay, so the question they ask is, well, the figure here shows a portion of a circuit. What are the magnitude and direction of the current I in the lower right-hand wire? Well, that current I is going to be 8 amps, and we could also tell that it is flowing to the right. Okay, now just to again, we're not doing any problems with this. We're just trying to give you the general flavor of where we're going with this next week. Now we talked about the current. The current is where you just look at a cross section and then you just count how much charge is going through the whole surface per second. And that gives you units of amps. And so your I, your current, is in coulombs per second, which is an amp. I being current. Now the current density tells you how much current is flowing through a cross-sectional area, but it tells you about how much current is flowing at each section. So we could just look at one point here, and then J would be more like a flux, current per area. And then if you integrate that over this surface area, you would get the current. So if you take the current per area, so this is going to be in amps per meter squared, and dot product it with the surface, so these are again going to be vectors pointing out of the surface like we used when we were doing flux, then we would get something that's a current. So this is going to be in amps, which of course, just to really reiterate it, is coulombs charge passing by per second. Now, something that's sort of interesting is that if we just thought about having a bunch of charges floating around in space and you accelerate them, there's no reason for the current not to just increase and increase and increase and get faster and faster and faster. Because if you put an electric field, that causes an acceleration. However, in the sort of the classical theory of this, what we think about is that the metal is not perfect, and as the electrons run through, they run into impurities and they accelerate for a bit and then they stop. And so what this means is that instead of just accelerating indefinitely, the charges have some sort of a natural current speed, or some sort of natural current that's dependent on the electric field at the point where they're being where it's being applied. So we to deal with this, and we're going to have to do this a little bit more slowly on Monday. We come up with two different quantities. One of them is called the resistance, and one of them is called the resistivity. And the resistivity is the ratio of the electric field to the current. So if I get a bigger current from the same electric field inside of my material, I would have a smaller resistivity. It doesn't resist allowing that current to flow through it as much. The same idea is going to apply for a bulk object. If you think about just having a block of something and you apply a voltage, so just to put our picture as we had it, here would be a battery. There's a voltage. The current would want to flow from plus to minus. We get some I, and the voltage difference is going to be across that object. And we think about this object as having some resistance. That's the ratio of the voltage applied to the current that goes through it. So if you have a small resistance, that means you have a bigger current. It resists letting the current through less. And one of the key things that we're going to have to understand on Monday is that the resistance and the resistivity are connected to each other. It's connected in the sense that if you have a longer tube, you have more chances for the electron to, the charges to run into impurities, so your resistance would go up. So that's why this is up here. And if you have a bigger cross-sectional surface area, that gives more paths for the electrons to get through. So if you have a bigger area, the resistance goes down. Okay, so we're going to that's where we're going with this next week. We're going to add in resistors, and we're going to start talking about current, the amount of charge that's flowing around in your circuit per second. Okay? So what have we shored up today? We talked a little bit about energy on capacitors. The energy of the capacitor depends on the amount of charge sitting on the capacitor squared. That's our U equals 1/2 CV squared. We talked about how current density and current describe how charges move through a circuit. The important thing to remember is that amps equals coulombs per second. So this is the unit of current, is a coulomb per second. How much charge is passing by a cross-sectional surface in your circuit each second. And because we notice that charge doesn't just simply get faster and faster and move more and more quickly through a circuit as you continue to apply a voltage, we need to start introducing an idea called resistance. So we're going to next week be talking about resistance and resistivity and how those are ways that energy can dissipate out of our circuit. Okay, so thanks for watching, and remember, homework, quiz, and reflection question, all due on Monday. And have a good weekend.